Hi, and welcome to Dr. V's AP Chemistry webcast. Tonight we're learning about the gas laws. We really want to look at pressure, volume, and temperature relationships for gases. These are concepts that come up frequently in any chemistry class. AP Chemistry students definitely need to know and understand these relationships. So what I'd like to accomplish in this webcast, I'd like to review Boyle's law, Charles' law, and the combined gas law. We need to know them conceptually. We need to know the equations that we can use with these gas laws. I'd like to state Avogadro's hypothesis, which is really helpful, and I'd like to complete some practice problems as we go. Let's start with Boyle's law, which was the first gas law to be stated historically. Boyle said, for a fixed sample of gas at a constant temperature, pressure and volume are inversely related. If we look at the picture models, that might help us to understand it. I've got a certain number of particles in my container. They're at a fixed temperature, so they're moving at some average speed. When I make the container smaller, I'm not changing the number of particles, and they're moving at the same speed. But because the container is smaller, they're going to collide more frequently with the container walls. And so, as the volume gets smaller, the pressure goes up. There's that inverse relationship that we talked about for pressure and volume. We can see this graphically. When the pressure is very, very high, the volume is low, and vice versa. Another way to look at Boyle's law is if we plot the volume of that fixed sample of gas versus 1 over the pressure, we get this linear relationship because pressure and volume have an inverse relationship. Now, we do want to understand this conceptually in terms of collisions and know what the graphs look like. We also need to be able to do problems with Boyle's law. And the equation form that we typically see for Boyle's law is stated P1 times V1 equals P2 times V2. We are assuming that the temperature is constant, and it's implied that the number of moles of gas are not changing. So this equation is worth knowing. Now I'd like to jump to Charles' law, which looks at volume temperature relationships for gases. If we have a balloon at room temperature, and then we pour really cold liquid nitrogen over it, the volume shrinks considerably. Charles' law tells us that volume and temperature have a direct relationship. We are assuming that the number of moles of gas would not be changing, so it's a fixed amount of gas. We're assuming that the pressure is constant here. But volume is directly proportional to absolute temperature. And by absolute temperature, I mean the Kelvin temperature. When we want to think about this in equation form, we could write V1 over T1 equals V2 over T2, because that shows us that direct relationship. We do need to remember that the temperature has to be in the Kelvin scale for the mathematical proportions to work properly. So you have to take your Celsius temperature, if that's what you're given, and add 273 to convert it to the Kelvin scale. Anytime you're working with the gas laws, your temperatures must be in Kelvin, or you will not do the problem correctly. Now, that actually comes from Charles' law. Charles looked at volume temperature relationships, and we can see as the temperature increases for the gas, the volume increases. We get this really nice linear relationship. But if we take the data and extrapolate it back to a volume of 0, which Charles wasn't able to do, he wasn't able to get his temperatures that low, and we are making the assumption that we're not going to liquefy the sample at any point. But if we do that and extrapolate all the way back, we actually get that 273 conversion from the Celsius scale to the Kelvin scale. The thing is with the gases is that it's very hard to change temperature and pressure of a gas without the volume changing. All 3 variables are really connected to each other. And so we're not very concerned about Boyle's law versus Charles' law in terms of who did what. We really want to be able to talk about the pressure, temperature, and volume relationships. And we usually do this with the combined gas law, which is often written P1 V1 over T1 equals P2 V2 over T2. Now, of course, our temperatures have to be in Kelvin, but you can use any pressure unit as long as it's the same on both sides. You can use any volume unit as long as it's the same on both sides. And it's really not that important that you know pressure-volume relationships are Boyle's law, volume-temperature relationships are Charles' law. If you know the combined gas law, you've got all of them right here. It's really convenient for lots of different problems. The law of combining volumes kind of fits in here as well, so I'm going to mention it because I can. Why not? At a given temperature and pressure, the volumes of gases that react with each other come from the coefficients of the balanced equation, the ratios of small whole numbers. This is really helpful when you're doing gas stoichiometry. And when I do my ideal gas law webcast, I'll have a whole thing on gas stoichiometry, and we can come back and revisit that. But if you're doing gas stoichiometry problems and the pressure and temperature aren't changing throughout your reaction, you can just use the coefficients from the balanced equation to figure out the stoichiometry. Very helpful. Avogadro's hypothesis is also worth mentioning here. Avogadro stated that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. That's what we're showing in the picture here. I've got 22.4 liters of helium and nitrogen and methane in my vessels here. And they're all at the same pressure, 1 atmosphere, and they're all at 0 degrees Celsius. Their masses are different, but they all contain 1 mole of particles under these conditions. Avogadro's hypothesis is really worth knowing. You want to be able to state this. There are times in free response questions from the AP exam where stating Avogadro's hypothesis is really the main piece of your answer. So definitely this is worth remembering. Let's go on and talk about problem-solving strategies, since AP Chem students need to be able to solve problems with the gas laws, and you need to be able to do it reliably and quickly and correctly. Let's talk about our problem-solving strategy. And anyone who's got me in class, you know I really like to emphasize being systematic when you work through your problems. You always want to start by listing what you know. What information are you given? What are you solving for? What equation is going to help you get that answer? What's the relevant formula? Make sure your temperatures are in Kelvin if they're part of your problem. Set up the problem. I always like to have my students rearrange the equation to isolate the variable that they need, and before they substitute any of their values. And I like to write down all my units as well and make sure they're all going to make sense. Then you get out your calculator. You can estimate your answer, actually crunch the numbers, make sure your answer makes sense, make sure that you have appropriate units, make sure you've got your answer reported with the correct number of significant figures. You really need to be in the habit of showing your work and setting it up correctly. Don't just jump to answers. That's not usually a good strategy. So let's do our first problem. A sample of oxygen gas at 2.66 atmospheres occupies a volume of 11.6 liters. If the pressure is decreased to 1.83 atmospheres, what's the new volume of the gas? Now, let's do a little thinking before we start. My pressure went down, so my volume should go up. I should get an answer that's bigger than 11.6. Okay, so let's start by listing out the variables. Always a good thing. So P1 is 2.66 atmospheres. V1 was 11.6 liters. All right. I'm given a second pressure, my final pressure of 1.83 atmospheres. And as I said, it went down. So V2 must be what I'm solving for. And I'm expecting an answer bigger than 11.6 liters. Okay. So we want to start with the equation. The only variables are P and V, so we can just use Boyle's law. We could use the combined gas law and just leave the temperatures out, but that really reduces to Boyle's law. P1 times V1 equals P2 times V2. Okay, we're solving for V2. We want to rearrange our equation to isolate V2. All right, I really strongly encourage you to do this before you substitute your values. You're showing your setup, you're less likely to put the wrong number in the wrong place. So now that we've got V2 isolated, all right, so P1 times V1 over P2, now we can substitute in our values. All right, so we put all our numbers in, we type things into the calculator. All right, make sure you show the complete setup for your work. That's really important. That's very much expected for AP Chem students. Have those good habits all along. All right, and I get an answer of 16.9 liters. All right, I had 3 sig figs in all my given values, so it's appropriate for my answer to also have 3 sig figs because I was multiplying and dividing. And I've got appropriate units. I am solving for volume. It makes sense that my answer is in liters. Great. Let's go on and do another problem. A sample of helium at 33 degrees and 0.85 atmospheres occupies a volume of 6.65 liters. What pressure will the helium exert at 21 degrees Celsius and a volume of 8.25 liters? All right, again, we always want to start by listing our variables that will help us to identify what equation to use. So I'm given an initial temperature of 33 degrees Celsius. I have to add 273 Kelvin to add 273 to that to convert it to the Kelvin scale. I'm just going to go ahead and do that now because I know I need to. P1 is 0.85 atmospheres. and the initial volume was 6.65 liters. So we're making sure we have all the initial conditions together. And then we were asked what the pressure is. So we're solving for P2, and the temperature at the final state is 21 degrees Celsius, but of course we have to remember to convert that to Kelvin by adding 273. So T2 is 294 Kelvin, and the final volume was 8.25 liters. Okay, so I've got P and V and T. Clearly this is a combined gas law problem, so we're going to take our combined gas law. We're solving for P2, so we're going to rearrange our equation to solve for P2 and isolate that. I always find, especially when I have 6 variables in my problem, rearranging first makes it a lot easier for me to put the right numbers in the right place, because it's really easy to make mistakes. I do it all the time. All right, now we're ready to substitute and evaluate. So we go and put everything in. So we put P1, V1, T2 over T1, which was 306 Kelvin, and my final volume of 8.25 liters. I substitute everything in. All right, I find with combined gas laws, it's a little harder for me to predict, my answer compared to my original value. But that's okay, because I can get out my calculator and do the math on the calculator. I notice that my liters cancel, the kelvins cancel. I'm left only with atmospheres, which makes sense. I am solving for a pressure after all. And I'm looking at my sig figs, and I've got, most of them have 3 sig figs, except for my initial pressure, which only had 2 sig figs. So I do need to make sure that I report my final answer with 2 sig figs. So I get a final pressure of 0.66 atmospheres. Great, we've accomplished a lot. We've reviewed the volume, pressure, and temperature relationships. We talked about Avogadro's hypothesis, and we did 2 problems. Way to go. All right, we'll meet another time.